This video is over the last part of Chapter 10. The PowerPoint is posted on Brightspace, and I'm starting with slide number 10. Just a reminder of the historical period. We're about to leave the period known as the Renaissance and enter what's called the Enlightenment. So people like Newton and Leibniz and math like calculus is just around the corner. At the moment, we're talking about people like Descartes and Fermat and Pascal. And so the title of the chapter, Analytic Geometry and Precalculus, is definitely leading up to that. I want to talk about three specific things here. One is a specific curve known as the cycloid, which was historically significant. Another is several methods for finding tangents to curves, which is obviously related to calculus. And the third is a very brief look at some of the earliest work in infinite series. First, the cycloid. So we have a circle of radius r, and it's going to roll along this flat surface. You could think, for example, about the tire of a car rolling as the car is being driven to the right. Now, on the circumference of the circle is imagine a fly, and the question is, what path will the fly travel as the car moves forward? So let's take a look. The radius here is 1 in this picture. And you can see that overall the fly is moving forward, but because it's on the rim of the circle that's going around, it follows this arc shape curve, which is called a cycloid. There it goes again. So this curve came up just before the invention of calculus, and it was used as a challenge problem between various mathematicians to others. For example, this part right here is known as one arch of the cycloid, and the question, what is the area under one of these arches? Turns out to be 3 pi r squared, where r is the radius of the circle that generated it. Or what's the arc length of one of the arches? Turns out to be 8 times the radius. Or if we take the cycloid and flip it over and just show the first half here, then I can imagine this being a ramp. And I'm going to put marbles here someplace on the ramp, different places on the ramp, and they're going to roll down to the bottom. My goal is to get the marble to the bottom in the shortest possible time. That's called the Tautochron problem. And I can put the marble wherever I want. And so the question is, will the blue guy get down there first? Maybe, because the slope is nearly vertical here, so it's going to move the fastest. But the yellow guy, even though it moves slower, it has less distance to travel, so maybe it'll be the winner. So let's take a look at a video of this. And this is looping over and over again. And what you see is that the blue, red, green, and yellow marbles get to the bottom at exactly the same time. It turns out not to matter where on the curve you start, the particle will reach the bottom at the same time. This is the only curve for which that's the case. So this is a very special thing indeed. Here's another way of looking at it. If we take the entire shape of the cycloid and make a wooden frame out of it, then I can put a ball anywhere on the left half and a ball anywhere on the right half. And by the properties of the cycloid, they'll always hit exactly at the bottom. They'll reach the bottom from the left and right directions at exactly the same time, which is a pretty amazing and cool fact. Second, let's look at finding tangent lines. So the whole thing that starts this is this blue curve, y equals some function of x. And I pick a point, P, on the blue curve, and I ask for the tangent line, shown in black here. What's the equation of this line that's tangent to the blue curve at the point specified? This goes back to Descartes. He said, well, I'm going to try and construct a special circle, pictured in lavender here. Its center is going to be on the x-axis, so I just need to find out what its x-coordinate is. And the special thing about the circle is that it'll be tangent to the given blue curve at the point of interest. Since that's the case, then the tangent line to the blue curve and the tangent line to the lavender circle at this point will be the same line. So I can find the tangent line to the circle, but that's easy. If I know the equation of the circle, I can certainly find the equation of this green line. And then because a tangent to a circle is perpendicular to the radius at the point, I can just find the black line to be the perpendicular to the green line. So things like slopes of perpendicular lines being negative reciprocals of each other and so on are useful and make this an easy problem if I can find this lavender circle. How to do that? Let's take a specific example, y equals square root of 4x, which I've written y squared equals 4x to keep the algebra notation simpler. And the point 1, 2 is on the graph of this function. So I'm interested in finding the tangent at the point pictured. First, let's get the equation of the pink circle in terms of its center. So the equation of a circle in general is x minus the x coordinate of the center, quantity squared, plus y minus y coordinate of the center, quantity squared, equals the square of the radius. So somehow this expression on the right-hand side must be the radius, distance PQ. Well, it's not drawn, but right in here is a right triangle, and the radius is a hypotenuse of that. So by the Pythagorean theorem, I can take the sum of the squares of the legs, and right in here is distance x2 minus, and the number x1 here is the number 1. So x2 minus 1 is the x leg of that triangle. And then the y leg of the triangle is 2 minus 0, quantity squared. Next step is to note that point P is on both the circle and the blue curve, in particular on the blue curve. And so when there's a y squared term here on the left-hand side, we can replace it by 4x. While on the right-hand side, I'm just squaring the number 2. The next step I label simplifying, but what I really mean is to expand out all of these expressions and then group them by powers of the variable x. So x2 is a number that is about to be found, but x is the variable. And so here's a x squared term, and then some coefficient times an x factor, and then a constant coefficient. Then here's the key step. Descartes says, let's make the circle and the parabola tangent to each other. For that to happen, the circle has to intersect the blue curve exactly once. If it didn't intersect at all, then of course it couldn't be tangent, and if it intersected twice, then it wouldn't be tangent. So we need it to intersect exactly once, and that's at the point where x equals 1. So I want this quadratic function to have a double root of 1. And so if I set this equal to something that clearly has a double root of 1, then I can solve for this number x2 that I'm looking for. Okay, let's take this x minus 1 quantity squared, expand it out, and then Descartes had another good idea called the method of undetermined coefficients. By the way, if you've taken differential equations, that expression came up. So the same technique was used in a different context in that class. And the method of undetermined coefficients says, well, on the left-hand side and the right-hand side, I have an x squared term on both sides, and so their coefficients have to be the same. 1 equals 1, check. All right, on the left-hand side, I have a linear term. On the right-hand side, I have a linear term. Their coefficients have to be the same. That means that this equation has to be true. And there's a constant on the left, a constant on the right. They have to be the same. So this equation holds. Now, I have two equations just in one variable, but fortunately they both have the same solution, x2 equals 3. So the right place to put this lavender circle is with its center at 3, 0. And then as we said, once we know the center of this circle, and a point on the circle, we can certainly find the equation of the lavender line, and then the reciprocal, a negative reciprocal gives the slope of the black tangent line that we're looking for. Here's another look at the same problem, actually. So this is a little later in time after Descartes. Two people working independently were studying curves that were generated by two combined motions. So here we're imagining that a particle, maybe a comet, for example, is traveling along the path of this parabola. And again, we want to know the tangent direction at any given point. Well, the thing about a parabola is that it's, at any point, its distance from the directrix and its distance from the focus are the same number. And so as this point moves along the parabola, the velocity vector in the direction perpendicular to the directrix and the velocity vector in the direction coming from the focus to that point have to be of the same magnitude. That keeps those two distances equal to each other at any given time, these two distances equal to each other at any given time. But then that means that the tangent to these to this parabola can be found by taking the angle bisector of the angle between the two vectors here, which is an easy problem to do. Another problem involving the composition of motions or two combined motions is the case of the cycloid. So here, the particle in motion is moving because of two reasons. One is the circle overall is translating to the right, and the other is that it's on the circumference of the circle that's rotating. So we combine the translational motion and the rotational motion. And now because this circle is moving along without slipping, the angular speed, the speed of motion around the circumference of the circle and the speed of motion of the car going forward have to be the exact same number, which means that the magnitude of the vector pointing in the direction of overall motion and the magnitude of the vector pointing in the instantaneous motion tangent to the circle are the same magnitude. So again, we can find the bisector of the angle between these two vectors, and that will give us the tangent vector to the cycloid. Very nifty idea, only works in special cases, but notice that we are finding tangents to certain curves without using any calculus ideas at all. These are clever geometry and algebra ideas. Finally, let's look briefly at summation of infinite series. So there is some evidence actually that Archimedes himself knew something about how to find the sum of an infinite series. But that's debated, and certainly there wasn't much happening between then and this time period. So some of the earliest work in infinite series then are by people, for example, Mercator, who was able to find an equality that says that natural log of 1 plus x equals this sum given by an infinite series where x can be any number between -1 and +1. So this is actually a useful series. If I want to know, for example, the natural log of 1.1, that would be to take x equals 0.1 on the left-hand side. And so we can come over to the right-hand side and plug in 0.1 for all of these x's, and that would give me an exact value. Of course, to compute that, I'd have to compute the sum of an infinite number of terms, which is not possible. And so what in practice you really do is compute the sum of the first 3 terms or the first 10 terms or however many you need to get the desired accuracy. The more terms you use, the more accurate your approximation gets. Gregory, another mathematician, found an infinite series for the arctangent function, again for values of x between -1 and +1. And this one generated a lot of interest because if you plug in x equals 1, well, the arctangent of 1 is pi over 4. But if I plug 1 in on the right-hand side, these powers greatly simplify, and I just get this series of constants. And so by taking enough terms of this infinite series and a finite number of terms, we can calculate pi over 4 to any desired accuracy, and therefore we can calculate pi to any desired accuracy. So remember, Archimedes working geometrically with many-sided polygons. Now we've turned the problem of calculating pi into a brute force approach. As long as you're patient enough to keep adding more and more terms of this series, you can calculate pi to as high of an accuracy as you want. It turns out, though, that this series converges so slowly that this is not really a practical way to do that, but it spurred the idea, and then later other more series were discovered that converges faster. And last thought, when you took Calc 2 and talked about infinite series, one of the big deals was convergent or divergent. At this time, these mathematicians really didn't know what a infinite series was and what convergence meant. They were able to do useful things with these expressions, but the actual rigor of testing series for convergence would come a little later. And we'll stop there.